Let me just test. Okay, it's working.
So the last speaker today is Ysla Adans, and she is going to talk about how to find in an efficient way integrable deformations.
So thank you, everybody, and thank for the organizers for putting this very nice conference. So today I'm going to talk a little bit about the only I and the last D of the conference. So I'm going to try to propose some more systematic way to find integrable deformation. This is a part of one ongoing work with Marius and Miguel that are here, and one previous work that with Tristan that relates a little bit what Saskia told us today. And the idea is to give some motivations, talk about these deformations, see how this happens in our probe model. There is the XXZ spin chains, and try to show a little bit of results for the Hubbard model and give you some conclusion. So the idea is quite simple. We all like integrable models. They are very nice, has solvability and another nice features, but they are also very sensitive. So every time you try to add something that represents a little better the real world, you lose integrability and you lose your features. But we know that deformations exist. And in this way, we are trying to see at which point I can keep the integrability by adding deformations and how these properties will change our model. For this is good to know that in the recent years, I think that everybody has shown that the classifications of R metrics for spin chains has improved a lot with the boost operator method. So for example, now we have all the 4x4 regular and non-regular models classified. And during these classifications, some deformations appears as, for example, ADS, CFT, or XXZ deformations of the spin chains. And this is very nice, but you have to do the full classifications and then find the deformation. So it's not very practical if you are only interested in the deformation itself. Also, in the level of the charts, there also has been a lot of work in deform the charts by adding long-range deformations or try to construct new charts with the boost operator by several authors and see how this modify integrability. So the idea is try to combine these two things to use the boost operator method to find a systematic classification of only the nearest neighbor deformations, so I'm not taking long range here, of integrable models. So in order to do this, I have to introduce a little bit of our notations. And the idea is quite simple. You're just gonna take some Hamiltonian that you know that is integrable, and you promote this Hamiltonian for a new one that is deformed in these epsilon parameters by adding this piece here that are completely random metrics and try to determine which things you have to put here in order to keep this integrable. So for do this, one nice way that you can work is to use the boost, and the boost can give you, if you have your Hamiltonian density, the first two charges, the one is for free because it's basically just summing the Hamiltonian of the spin chain. So if you just deform, for example, to first order here, Q2 is only deformed to first order, but Q3 that is given by the boost has one part that is given by the commutator in different sizes, plus some G that is a range 2 operator that should be determined, can have higher deformations than Q2, for example. So you have Q2, you have Q3, and we know that a necessary condition for integrability is basically the Q2 and Q3 commutes. So we're going to impose this. And this is the part that sometimes using the boost gets hard, because this equation sometimes gets hard to solve. But as we have made the epsilon expanded, this become a little more simple because now you can split this in order by order in epsilon. So the first zero order you get for free because your model is integrable. This should be satisfied. And the first order equation is very simple. Basically, you just have to commute Q2 and Q3 and the other way around in different orders. And this will give you some constraints that are linear in both H and G. So when you solve this, you find a closed model, what is very good because you can take this model and now put at the second order, like an iterative method. The second order is a little harder because now you have quadratic terms in the first order deformation and new terms in the second order deformations. So you have to solve for both variables and obtain constraints to H2 and G2 and also for HI. And with this, you can continue in the same manner and extend these to high orders. So with this, we have to apply this method to some model to see if this works, how hard it is. And in order to do this, you're gonna get three different categories. The first one are the integrability breaking ones. It's some deformation that you add at first order is already failed. There is no way you can save this model. But you can also get something that is fully integrable in deformations. And this can be like a straightforward integrability. One simple example is going for xxx to xxz. If you add the z part is fully integrable, you don't have to do nothing. But you can also have models that you have to keep adding deformations order by order in order to make this integrable. So you can have these two types of integrable deformations, but you are also interested in something that lies in the middle between these two categories that are the quasi-integrable models. So are some models that can be integrable up to some others, but there's nothing you can do and add in order to make them integrable up to that point. So let's see how this works with an example. And for this, our problem model will be the XXZ spin chain. So it's the XXZ we will know and love with some deformation parameter here and represent in terms of the R metrics. So I'm gonna just take this input in my previous framework and I'm gonna get to, at first order, as I told you before, just get one closed model because there are linear equations. And you can see that this is the deformation that I can add to XXZ in order to make this integrable to first order. Obviously, you had to get XYZ. You get one spin term that is only in the Z direction. This is because of the homogeneity that you put in your problem. Now only the spin Z direction is conserved. You have three terms here that are symmetric terms that mix the spins, and they all appears, but the only term that is antisymmetric that appears in these deformations is with X and Y. Again, because you have put asymmetry in XXZ. So this is fine. I have the deformations, but all of them are fully integrable. So now I take the same model and put at a second order. And when I do this, I get two different models that I'm calling here model A and model B. So for model A, one interesting thing already appeared. You don't get XYZ anymore. So XYZ is not contained here. You get a three parameters model that is basically only the spin and the two of the symmetric and one of the unsymmetric exchange. But for this model to be integrable, you have to keep adding deformations order by order. So this lies in the second category, that in order for you to have full integrability, you have to add more and more deformations. The other model we have is much more simple. That is a model B. And in the model B, you actually get XYZ. That is basically, if you try to solve the higher order equations, you keep getting the same constraints, and you get a model that is basically the combinations of the spins in all the directions you want. That is basically saying that this deformation is a rotate XYZ model. So it's good because you have found the deformations, but all of this is known because, as I told you before, 4x4 integrable models has been classified. The new stuff here is this quasi-integrable model. This quasi-integrable model are a model that at first order is fine in respect to integrability, but if you try to extend this to second order, there is nothing that you can add in order to make this integrable, so it breaks integrability. So it's something that is the XXZ, some term here with the alpha, that is the XYZ part, they spin in that direction, and this unsymmetric term that is known in the literature, like the DMI term. And the really interesting stuff in this is that if you take each of these terms separately, they are integrable. but if you put all together, you lose integrability. And also, these terms here really represent some models that appear in condensed matter in nature, because this can create, for example, ischemias in your model that is rotating the X and Y directions. So it's good. I find this model Q2 and Q3 only commute first order, but this really means something. So in a more integrability framework, we could test this by trying to find some R matrix correction that works for this quasi-integrable model, and we have find this correction here for the R matrix. As you can see, it's of non-difference form in these beta terms. It's also satisfied braiding unitarity, but the nice thing about this is only respecting Young-Buster up to first order. So you can try whatever you want to add this at the second order, try to plug it back in Young-Buster equation, you're not finding a solution. So in this sense, this model really is quasi-integrable. And with this, if you try to make this fully integrable, you either go to model A or model B. This is in terms of the integrability framework. But do this have any new physics? So in order to do this, I'm gonna show some very light spectral statistics, and now I thank Saskia for introducing everything that I need before. So I'm going to compute the level spacing, that is the difference between energy eigenvalues for this model, this quasi-integrable model. And as Saskia told you before, if you try to fit this in some distribution, usually if it is possible, you get integrable models. And if it's another thing like Wigner-Dyson distribution, you get something that is chaotic. So how this quasi-integrable model fit in this scenario? So you have compared this quasi-integrable model to some really integrability breaking model and try to see how these two systems transition to chaos if they go in a different way, because you know that both go there, but we don't know how they go. So in order to answer this, we're gonna try to fit these two models in a more broad distribution, that is a broad distribution, that contains either the Poisson distributions for omega equals 0 or the Wigner-Dyson distribution for omega equals 1. So our regime is, if omega is 0, I'm in the integrable regime. If omega is 1, I'm in the chaotic or non-integrable regime. And we compare our models with this. So as you can see, this blue one is the quasi-integrable one. The orange one is the integrability breaking one. For the integrability breaking, it goes almost straight from chaotic, or from integrable to chaotic. You just turn on the deformation parameters and whoop, it goes. But for quasi-integrable model, it goes much more smoothly. You even have some region here that your integrability is being preserved, you can say. And also something that you can look at this and ask is, okay, and what about when I make my spin chain vary the length? So in order to do this, to analyze how this scale with the spin chain size, we can define something that is the midway, the critical coupling, whereas I'm in the midway between chaotic and integrable. So I want to see when my models reach omega equals half. And when you plot this with the length of your spin chain, you can see this is from the integrability breaking model. So you go very fast to this critical coupling. But for the quasi-integrables one is much more smoothy. And you try to fit this in some dependence with L in a fit to a parallel scaling, something like A to L2 minus B. And what you get is that this B, that is the important part, is like 2.5 halfly. And this is really interesting because this line between the strong integrability breaking cases that you have in the literature, that you add like a random deformation to integrable model, see how this model breaks integrability. In these cases, you have -3. And the weak integrability breaking that Saskia shows you today, that you keep adding deformations with higher range, and in the end, if you add everything is in fully integrable, is go to -2. So this model really lies between these two cases and is showing some new features, some new physics. So this is something that you want to look for, it's not just a curiosity. So we probe this with the XXZ, that is easier, is more interesting because we will work with this every time. Can we do this for a more complex model? So in order to do this, we take the Hubbard model. Why? Because Hubbard has a lot of free parameters for us to play about, and also because it has a lot of physical relevance, both for the high energy community and the condensed matter community. So we just take our usual Hubbard model that has these terms here that are the jumping terms with two species of fermions, up and down, 1 and 2. You call it what you want, and some interaction between these fermions. And in this case, we choose a parameterization that has a shift in the energy, where these C's and C daggers are the usual creation and annihilation operators given by these algebras. And alpha and beta are the species here. And what you have to do now is a fermionic model. You have to make this a spin chain. And for this, I'm not giving the details, but we use a Jordan-Wigner transformations and map the local space in a C2 times C2 Hilbert space, where every time I'm saying that my sigma is in the first site, I call in sigma. These are the up spins. And every time sigma is in the second site, I call this tau. They are related to the down spins. So now I have a Hubbard model that is written in terms of the spin, like a spin chain. So with this, we can apply our machinery. So of course, this is a 16 by 16 model. If I try to do a full deformation at once, you have a lot of degrees of freedom. It will be very hard to solve at higher orders. At first order, not so much. So at first, we work with some ansatz that requires that the numbers of the fermions are preserved in this deformation, so I cut by a half, and I apply all the machinery and obtain the Hubbard deformations. So the first order Hubbard deformations, I mean, split in 3 different parts, H alpha, beta, and Q, where the first part, the H alpha, has terms that you would expect to appear in the Hubbard deformation. So for example, you have some numbers operators that you can add, or some interaction terms that you can add to a Hubbard model, and some jump operators here that already appear in Hubbard, but now you have more degrees of freedom to make these coefficients be different here. The next part, that is the 8 beta, is a little more interesting because now you have doubles, creation and annihilation interactions. Of course, they are in different sites, so you can create and annihilate different species in different sites of the Hubbard model. And also, you have something that is not only a flip in your Hamiltonian, but it also makes a flip and a jump. So now you can have more things happen in your Hamiltonian. And HQ has a bunch of weight jump interactions. So it's the same jump that it happens in Hubbard, but now they are weighted by difference of different species or interactions between species. You can get the whole thing here. So you have 16 parameters. These at first order. So now I take this thing and put at second order, and I get 3 different models that has higher order integrability. And these models are really nice because they are really symmetric. If you look at this HQ here, they have like these 3 less in this 14, 15, and 16. And to get fully integrable models, the rule you have to have is that you put 2 by 2, you make a reduction. Either 16 and 15 get reduction, or 16, 14, or 14, 15. And one check we have made with this model is, for example, model B, you can fit Alcaraz and body F Hubbard deformation inside of this model. And the other ones cannot be fit, so they are really different. We compare them by base transformations, parity, discrete transformations, and so on. There are more results about Hubbard, but I'm just showing you these ones. And now, in summary, what you have found for Hubbard is that you have 2 parts that are integrable. You don't have to add any additional constraint to them. But there are other 2 parts, other 1 part, the HQ, that either is the quasi-integrable one, if you don't add any constraints, if you keep your 6 parameters. But if you reduce your constraints, you get 4 parameters and it's fully integrable. So you have the whole picture for Hubbard here. Also, there are second order deformations that I'm not showing here because they would take like 3 or 4 slides. But in the end, what you get is that this boost is really a nice thing that you can use this to classify these integrable deformations, because you take a problem that is very difficult and split in others that is a thing we usually do in physics. And with this, you can find, for example, these quasi-integrable models that has new physics for XZ spin chain. You can even work with models with a huge number of parameters like the Hubbard model. And when you study this, you can really see that this quasi-integrable deformation is something that is between the weak and the strong integrability breaking. And right now, some outlooks, we would like to study a little more what this deformation, this quasi-integrable one, represents, is possibly to make schemas or something more physical about this. Is this DMI term. The full Hubbard classification is something we are working on, because first order is easy. For higher orders, to get a little more break, but I think it's doable. And this other part is because Hubbard is connected to ADS-CFT, for example, but it's not this Hubbard, it's a Hubbard with a twist. And turns out that twist spoils the deformations. So you have to be very careful while you're studying this. So it will be nice to see this other side of the Hubbard. And with all the deformations of Hubbard classified, we finally arrive at the twists. So you know that different twists give you deformation. So we would like to compare this boost operation with the different ones and see which one you can obtain with different and which one not. And with this, I thank you, and I'm open for questions.
Thank you, Ysla. Questions?
Thanks for the talk. So for these quasi-integrable models, where you break at some finite order,
Yeah.
I suppose the order at which you break should somehow play a role in this order of L, this exponent of L that you found.
Yeah, I think it might be. I'm not saying anything about this because I cannot be sure, but I think there might be playing some role. Here we just break at first order, but you could add, for example, the second order deformation and see how it break.
Yeah.
I think it could follow something. I think that much more terms you add, much more closer would be like for the weak integrability breaking one, because it's the same thing. It's something that I cannot make integrable up to the whole thing, but much more terms are add much. I think the coefficient will be closer to -2.
Kind of a related question. Why should it be power law scaling?
What?
Why should it be power law scaling? Yeah.
It's a fit. We also did another fit that goes like L log of the L, but this was the fit that was better, and also we could compare with these other two types.
So there is no kind of theoretical justification for this fit.
Yeah, to try. Yeah.
Well, maybe another question. Do you impose hermeticity condition on?
Yeah, this is Hermitian one, but you could impose no Hermitian. Yeah, because yeah.
Okay, thank you. More questions?